Hello students, in previous video we talked about torque acting on magnetic dipole in magnetic field and frequency and time period of its oscillation. In this video we will address last two questions of assignment 5.2 that is potential energy of magnetic dipole in external magnetic field and Gauss's law for magnetic field. So let us start. We know that to produce magnetic field in this manner, we have to have north pole on left side and south pole on right side. So let me consider magnetic field from left to right, and in this magnetic field we will place bar magnet. So what if I have bar magnet placed like this, say north pole here, south pole here. What if I have bar magnet placed in this manner where north and south are like this? So we know that if m direction, that is the direction of magnetic dipole moment, and B is from north to south, so this is B when angle is 0. Say this is the most comfortable situation for the dipole because south pole of the dipole is facing north. Okay, and north one is facing south. So if I call it figure 1, uh, the potential energy must be minimum. So I can say that if theta is 0, what is theta? Angle between M and B, magnetic dipole moment and magnetic field. Potential energy should be minimum. Okay, and what about this case where dipole moment is from south to north? So dipole moment is towards left, from right to left, and magnetic field is from left to right. So what must be the case here? This is the most uncomfortable situation because north of the magnet is facing external north. So I can say that when theta is pi, angle between M and B is 180, potential energy should be maximum. So this is our prediction. When we have expression, our prediction and the equation should be matching, should be supporting each other. And then if I consider third situation where dipole is placed like this, there should be tendency of the dipole to rotate. So this may not be most uncomfortable or most comfortable situation. So potential energy may assume some intermediate value between the minimum and maximum value. So let us try deriving the expression for magnetic potential energy. So we can define magnetic potential energy as force dot displacement, but in case of rotational uh, motion, it can be written as integration torque dot theta or d theta. So it is mb sine theta. M is the dipole moment, B is magnetic field, both being constant can be taken out. So it is this integration of sine theta gives us minus cos theta. So this is the expression for magnetic potential energy, or else we may write this as minus m dot b, because we know that a dot b is ab cos theta, so m dot b will give us mb cos theta. This is the expression for magnetic potential energy. Okay, let us check the special cases. What if theta is 0? So if theta is 0, cos theta will be 1. If cos theta is 1, potential energy is minus mb. Okay, that is what we predicted here. Minus mb must be minimum. What if angle is 180? If angle is 180, cos of 180 cos of pi is minus 1. And in that case, potential energy will be plus mb. That is the maximum potential energy. And then if angle is considered to be 90 or 270, in that case cos of theta will be 0. Cos of 90 or cos of 270 will be 0, and then potential energy will be 0. So you can say that minus mb is the minimum potential energy plus MB is the maximum potential energy. So if I have a dipole placed in external magnetic field, suppose I have dipole at 0 degree. Suppose dipole is placed in such a way that north is here, south is here. So what is the angle value? So we know that this is the direction of magnetic dipole moment. B is also in the same direction. So theta is 0. Now what if I want to flip the dipole? What if I consider that I want to flip the dipole? So I want to take it to 180 degree. And then how much work I'll have to do? So I can say that initial potential energy is minus mb, final potential energy is plus mb, and hence work done is 2 mb. So 2 mb work I'll have to do if I want to take it from this situation, theta equal to 0 to theta equal to 180. And what if I want to take it from 180 to 0 degree? In that case, work done will be minus 2 mb, because dipole will go by itself. You just have to flip it and it will go by itself. So by taking difference of initial and final potential energy, you can find out work done to rotate dipole. If you are asked to find out work done to rotate any dipole, you can check final and initial potential energy. Difference of the two will give you work done. Now, next topic today is Gauss's law for magnetic flux. But before that, let us check this answer. For magnetic dipole with pole strength m and length 2l, dipole moment is this, torque acting is m cross b, and then potential energy can be given as integration torque d theta. Substitute values, simplify, and you will end up with minus m dot b. And as I explained, theta equal to 0, theta equal to 180 are the special cases. In one case, potential energy is minus mb, in other case, potential energy is plus mb. For angle 90 degree or 270 degree, cos theta will become 0. Okay, this is cos theta, which is 0, and hence the potential energy will be 0. Let us move to next topic today, that is Gauss's law for magnetic field. Earlier in electrostatics, we had a topic of electric flux where we said that if you have some charges, say Q1, Q2, Q3, Q4, and if this is the closed surface, the flux linked with any closed surface can be given by closed integration E dot dA, which is equal to sigma q by epsilon 0. This is for electric flux. And what is sigma q here? Sigma q is the charges enclosed by the Gaussian surface. Now, similarly, in case of magnetism, for flux enclosed, the formula is B dot dA is equal to 0. Now, actually, instead of sigma q, you have magnetic pole, and instead of epsilon 0, you have mu 0. So, the formula should have been B dot dA is equal to mu 0 sigma m, because role of charge is now played by magnetic poles. Instead of positive charge, we have north pole, and instead of negative charge, we have south pole. So why the shape of the Gauss's law for magnetic flux is not this? The reason is we don't have single north pole or single south pole in existence. So whenever you take magnetic poles, they always exist in pair, and hence if you sum up the net pole, it will be 0. And hence the Gauss's law for magnetic flux says that if you take magnetic field, if you take integration of magnetic field over closed surface, the answer will be 0. And what is the reason? The reason is magnetic monopoles don't exist. Otherwise the answer would have been this. Okay, but as magnetic monopoles don't exist, the answer is 0. So this is the Gauss's law for magnetic flux. Statement is the net magnetic flux passing through any closed surface is always zero. As the magnetic field lines form closed loop, the field lines entering the surface is equal to field lines leaving the surface, and hence magnetic flux will be zero. Meaning of this line is that suppose if I consider a north pole and south pole like this, and suppose if this is the Gaussian surface, my argument can be that whichever number of field lines are going out, the same number of field lines are coming in south pole, and hence what is the net number of field lines linked with the surface? Zero. What if you consider this shape of surface? Suppose this is my Gaussian surface. Now if I say that field lines are just going out, I am wrong, because whichever number of field lines are going out, same number of field lines are coming back from south pole, and inside the magnet field lines go from south to north. Okay? And it is not possible to separate south and north pole. Individual north pole or individual south pole don't exist. Magnetic monopoles don't exist, and hence number of field lines leaving is equal to number of field lines entering, and hence net flux is always zero. So that was the topic. I hope you could understand. Thank you.